Hi everyone. Today we are going to be talking about some different gas laws besides Boyle's law. So Boyle's law is looking at pressure and volume, but there are other variables about gases that are measurable that we want to talk about. So to start off, we're asking the question, what happens to the volume occupied by a gas when you heat it up? So remember that heat is kinetic energy. So if you increase temperature, you're going to increase the kinetic energy. And as that kinetic energy is increasing and those gases are moving faster and faster, they're spreading out, which means you're increasing volume as well. So what we're learning today are two different gas laws called Charles' law and Gay-Lussac's law. So they're going to be utilizing different variables than we saw with Boyle's law. And there's a couple things we have to keep in mind when we're working with these. So we're going to talk about Charles' law first. So Charles' law is looking at the relationship between volume and temperature. Volume goes up, temperature goes up. This is a direct correlation, okay? If volume goes down, temperature also goes down and vice versa. Key here is that temperature has to be in Kelvin. So if you're in Celsius, you have to convert it to Kelvin. It is not permissible to use Celsius. The equations will not work properly. So to do Kelvin, let's see. In order to convert to Kelvin, it's a pretty easy conversion to do. If you're in Celsius and you want to convert it to Kelvin, you just add 273. If you are in Kelvin and you want to go back into Celsius, it's negative 273. So let's say we have 20 degrees Celsius. In Kelvin, you would add 273. So that would be 293 Kelvin, okay? So it's just as simple as that. So Charles' law is that first law we're looking at. And with Charles' law, the volume can be in any unit you want. Doesn't matter, it just has to be the same on both sides. However, the temperature must be in Kelvin. So that is a non-negotiable, got to be in Kelvin. And then we're assuming that pressure and amount of gas are staying consistent. So Charles' law specifically stated is that you have this direct relationship that's occurring. So as volume goes down, temperature goes down. As volume goes up, temperature goes up. So they are going to be directly correlated with one another. So let's try this first example. So we remember that Charles' law is V1, T1, V2, and T2. So we're looking for two volumes, two temperatures, and we just have to keep in mind the temperature has to be in Kelvin. So I read through my problem. It tells me I have a gas that's occupying a volume of 225 mLs at a temperature of 20 degrees Celsius. So that is going to be my first volume and my first temperature. Then it asks me to determine the new volume of the gas if it's heated to 30 degrees Celsius. So that's my second temperature, and the new volume is V2, which is my unknown variable. So that's the thing that I don't know what it is. So what I want to do is take my numbers, plug them in, except I have to turn the 20 degrees Celsius into Kelvin. So that's going to become 293 Kelvin because we're adding 273. And then the 30 degrees Celsius is going to become 303 Kelvin. Again, you're adding the 273. So you put your initial volume, the 225, over that initial temperature, 293. V2 is our unknown volume, and T2 is 303. So you just solve this algebraically. So I just solve the fraction on the left side. That's 0.7697 equals V2 over 303. Then I'm going to multiply both sides by 303 to get rid of that in the denominator, so those will cross out. So then V2 is equal to 232.7 mLs, incorrect sig figs, 233 mLs. So looking at another problem very similar to what we just saw using Charles' law, now we have a sample of neon gas that's occupying a volume of 3 liters at 35 degrees Celsius. It's then increased its volume to 3.10 liters, so we want to try to figure out what the new temperature is, okay, that new Celsius temperature. So if I remember, my equation is V1, T1, over V2 T2. I have V2, I have, T1, and I have V1. My unknown here is going to be this new T2. That's my questionable one. So my volumes are both in liters, so that's good. And the only thing is I want to turn that 35 degrees Celsius into Kelvin. So I'm going to add 273 to it, and that becomes 308 Kelvin. Okay, so now I'm at 308 Kelvin. Now I'm ready to go start plugging stuff in. So first volume is 3.00, first temperature is 308 Kelvin, second volume is 3.10, so we increase slightly. T2 is our unknown variable. So I'm going to do what I did last time, solve things on the left. So that is 0.00974 equals 3.10 over T2. If I'm trying to solve for T2, I have to get it out of the denominator, so I'm going to multiply both sides by T2. Let me kind of scroll down here, running out of room. So 0.00974 times T2 is equal to 3.10. I want to get T2 by itself, so I'm actually going to change my color. I'm going to divide this by 0.00974, same thing on this side. And what I find, T2 is equal to 318.3 Kelvin in correct sig figs. This is, oh gosh, I guess I need 2 sig figs. And this would be, I don't know why I have this written here. So because you need 2 sig figs, I would change this to 3.2 times 10 to the second Kelvin, okay? So essentially 320. So this makes sense because our volume went up slightly, our temperature also goes up slightly. So that's to be expected. So we're following the laws of Charles' law, so that's a good thing. So the next law that we're also looking at is what's called Gay-Lussac's law. So here we're looking at pressure and temperature. And again, you can see it's set up very much the same as Charles' law. It's a direct relationship. Here we have to have the temperature in Kelvin. We're assuming that the volume and the amount of gas are constant, and pressure can be any units you want, just has to be the same on either side. So if we're looking at this relationship, it's going to be a direct correlation. As temperature goes up, pressure goes up. As temperature goes down, pressure goes down. So just keep that in mind. So we're going to try one practice problem. These aren't too terribly difficult because Charles' law is essentially the same math, just different variables. So Gay-Lussac's law is pressure over temperature. You have your initial and then your final. So we're going to read through the problem and see what we have. We have a gas that's exerting a pressure of 845 millimeters of mercury at a temperature of 40 degrees Celsius. Determine the new pressure if it's cooled to negative 15 degrees Celsius. So I've got my initial pressure, I've got my initial temperature, I've got my final temperature, and P2 is my unknown variable. So first thing I have to keep in mind, I got to get these 40 degrees and negative 15 degrees into Kelvin. So I can't have them in Celsius. They've got to be in Kelvin for this problem. So 40 degrees becomes 313 Kelvin, and negative 15, 258 Kelvin. And remember, to get Kelvin, we're just adding 273 to our Celsius measurements. So I'm going to plug in my numbers and see what I have. So 845 millimeters of mercury is our first pressure. Our first temperature is 313 Kelvin. We don't know our new pressure, and our new temperature is 258. So I'm going to solve what's on the left, which is going to be 2.699 equals P2 over 258. I need to get P2 by itself, so to do that, I'm just going to multiply both sides by 258. And what I end up finding is that P2 is equal to 696, and in correct sig figs, 700 millimeters of mercury. Okay, so hopefully by this point you understand how to use volume and temperature, which is Charles' law, and you understand pressure and temperature, which is Gay-Lussac's law. So both of these you need to know how to use those measurements, and just keep in mind that you've got to be working in Kelvin for both of these.